We're going to take a look at now protein secondary structures. Right? So we talked about primary structure being sequence. We talked about amino acid structures. Right? Now again, you don't have to memorize the amino acid structures for me, but you do have to know the names of the amino acids and what are their properties. For example, you should know that aspartic acid, it's an acid, so it has a carboxylic acid group. You should know cysteine is a thiol, okay, it's a SH, right? So you don't have to know the exact structure, but you should know what kind of functional groups are on the amino acids such that they have or they have not just a, but they have many different properties for them that allows them to have some functions inside of a protein. Okay, so you should know the amino acids functional groups, okay? Coming back to protein structures, protein molecules have 4 levels of structural organization. Primary structure we talked about, so that's essentially the amino acid sequence. Nothing more than that, simple. Alanine, glycine, blah, 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 okay? And then we're going to talk about secondary structures today, okay? So secondary structure, which is essentially the local folding of amino acids into regularly repeating units, such as alpha helix or beta sheets. So these are 2 of the most dominant or prominent types of secondary structures you have. You also got turns and some other types of helices that we'll talk about. But most of the time you hear a lot about this alpha helix, that alpha helix, this helix, that beta sheet, that kind of stuff. Okay, so these 2 are the prominent secondary structures for proteins. Tertiary structures we'll also talk about. That's the overall folding of monomeric protein or subunit. But we will not really get into a lot of details regarding tertiary and quaternary because tertiary and quaternary is very specific. Okay? They have different names, different motifs. Okay? So if you guys take a class in a more advanced biochemistry course, we'll talk about those. Okay? But essentially, tertiary structure is where you have multiple like alpha helixes, multiple sheets. Together, they form a larger type of structure, like barrels, like some hot dog fold, donut shapes, those type of things, right? So those are tertiary structure. So tertiary structure is still talking about monomeric proteins, but in reality, a lot of your enzymes are all like dimers, tetramers, dimers of tetramers, okay? They actually have subunit and subunit interaction, okay? And then they form a functional protein, okay? So those interactions are then called the quaternary structures, okay? Associations of subunits, okay? For example, if you look at this large picture, you have the blue, you have the green, you have the red, all of them coming together and form a macro structure. That will be the quaternary structure. Cool? So primary, secondary, tertiary, quaternary. Primarily, in biochemistry, in undergrad level, we primarily focus on primary and secondary. Now, coming back to this, the structure of a peptide bond. Okay? A while ago, remember, I think it was like 2 lectures ago or 3 lectures ago, I mentioned that in amino acids, or actually in polypeptides, where you have C alpha and C alpha, okay, they form a plane, okay, just like what you see here. They are the diagonal, this C alpha and this C alpha, they are the diagonals of a particular plane, okay? So the 6 atoms on this plane, you have 1, 2, 3, 4, 5, 6. These 6 atoms essentially are coplanar. So as a result, okay, so they don't really move too much. Right? They don't really move. For example, this bond, this particular bond doesn't rotate, right? Because if it rotates, then your C alpha, this guy, and this particular C alpha, they're not going to be in the same plane, for example. So they don't really rotate. Right? So I'll show you what actually rotates and then what actually moves today. Now, very briefly, you saw this a couple days ago, maybe last week or 2 weeks ago, about the whole cis and trans conformation. Your amide bond can move, but essentially it only has two states, the trans state and the cis state. Okay, why is that? Because this particular, so this guy, this guy, this guy, this guy, this guy, and this, these six are in a plane, remember? Okay, so that as long as your nitrogen with all of the rest of them are in the same plane, that's okay. However, the cis conformation is not favored because obviously the R groups will hit each other. You have steric interference. So cis is usually not favored. You want to have trans. So what that tells you then is you have the R group facing two different directions. Now, this is actually what I want to show you. So because between C alpha and C alpha is a plane, so the planes don't move, but between the planes you can move. So what you can actually move is at the C alpha. Okay, you can actually have sort of angles twisting. So which bonds can move? This guy and this guy. All right, so let me show you a better picture. So we define this phi and psi, okay? The angles between the carbonyl carbon to the C alpha we call phi. The angle between the nitrogen and the C alpha we call psi. Okay, so with C alpha at the center, you can have two angles, okay, because they're literally two planes, right? So you can have, for example, two planes, and then in the middle, that's where they join. That's C alpha. So you can twist them. Okay, you can twist them. Okay, that's the angles that we're talking about. If you twist that guy, it's phi. If you twist this guy, it's psi. Okay, so you can twist them. Now, of course, you can twist them, right? Proteins will not stay like this forever because that's going to be a linear protein. That doesn't work. So you actually have some localized angle such that they form secondary structures. Okay, so actually this is where the secondary structures come from. Okay. All right, so you have to know this. Okay, you have to know what I mean by psi and what I mean by phi. Okay, so it's essentially where you can twist is at the C alpha. Okay, the alpha carbon. So any amino acid is always you have the carboxylic acid group, right? And then a carbon right here. This guy is the C alpha. It's called alpha because it's alpha to the carbonyl. Okay, and of course you have the amino, and then you have a hydrogen and an R group. Okay, so let's just be clear. C alpha is that extra carbon next to the carboxylate, next to the amino group. Okay, so that's the C alpha, right? I'm not going to say this again. Okay, so C alpha, remember that. Essentially, what can rotate, which bonds can rotate? So this bond and this bond, they can move, okay? Because if they move, the plane moves with it. Make sense? A positive rotation is clockwise seen from the alpha carbon. So from the alpha carbon out, positive is counterclockwise. So I have where the junction, this point, that's the C alpha. Okay, so from C alpha, clockwise is positive direction, counterclockwise is negative direction. Make sense? We're cool. Okay. All right. So simple. Okay. So this is easier than calculus, I bet you anything. All right. Right. So now, obviously, you can have positive 180 and negative 180. I mean, come on. If you go like this, right? 180, it becomes like that. Okay? And then if you keep on rotate, that essentially is the negative direction. Do you guys even know what I'm saying? 可以哈？你确定听得懂？不要骗我哦。就是 你这样转是正的180嘛，然后转到180，然后你再继续转，那就是负的啦，就是等于负的180嘛，可以哈。Okay. All right, so we're cool. So obviously the angles will be positive to minus. Okay, so it's positive 180 minus 180. Okay, so the extended formation of the chain shown here corresponds to plus 180 and plus 180 that. Okay. By convention, when both phi and psi equal to 0 means that the hydrogen and the oxygen of the next carbonyl, they completely overlap. So obviously there's no such thing. Okay? There's no such angle as 0, 0. Okay? You cannot have this because this is only a convention. Right? By convention, it means that they rotate, become like that. Okay? That's not allowed. That's not allowed. Okay? So 0, 0, that doesn't happen. Okay? Make sure you know that. Because why it's not allowed? Because obviously your amino hydrogen is hitting the carbonyl oxygen. So it's not okay. So having these angles are really useful for us when we're talking about secondary structures. Why? Because if you go out and you grab a bunch of different proteins and different protein structures and then you look at what are the allowed phi and psi, you can see how they cluster at particular angle combinations. So you take a bunch of natural enzymes and then you look at the allowed phi and psi, the natural phi and psi angles, and you will see how they are usually going to be clustered among certain places. And here what we have is a Ramachandran plot. Okay? It's a graphical representation of allowed phi and psi angles. Now for every amino acid, they have a specific phi and psi that are allowed and the probability that they're found in such a position. Okay? So for example, glycine is this. The R group is just a hydrogen. Okay? So it's very small. So the R group, because it's very small, so you can rotate a lot. Okay? So this guy can rotate a lot, that guy can also rotate a lot because you don't have an R group essentially. And you don't have an R group, it's just a hydrogen, so that you can pretty freely rotate. So glycine is very flexible. The available structure that proline has in terms of rotating the phi and psi angles will be limited. Right? So therefore you see the available phi and psi, what you see is very clustered. Okay? They are found in very specific angles. Okay? They don't have, for example, you don't have any of the psi angles in the positive direction. You can't have that for proline. Okay? You can only have it in the negative. Yeah?
So is it because of spherical elements?
Yes, but I want to say it's more related to the fact that your nitrogen cannot rotate in this case because it's linked together. Okay? But in general, that is true. Okay? So if you look at different amino acids, and some amino acids have very clustered or very constrained available angles, that is because the steric hindrance between the R group and the other elements. Yeah, so it is because of sterics. Okay, but in proline, obviously, in addition to sterics, you see how the nitrogen is restricted. Okay, so the C alpha, the next C alpha with nitrogen, it's going to be restrained between the available angles that they can have. Right? Okay, so glycine is very flexible. All right, so if we're looking at the natural secondary structures, okay, and I'm just going to tell you right now, you have alpha helix and beta sheets. Okay, so alpha helix, beta sheets. So if you take a look at a general Ramachandran plot, okay, and you see what are the available locations, what you can see is alpha helix, the right-handed alpha helix, is generally found when your amino acids, regardless of which amino acids, okay, when they have phi and psi angles around this region. Or when you have beta beta sheet generally has a phi and psi angle towards the top left. So what this tells you is when your amino acids, when they have this phi and psi angles, they tend to form beta sheets or alpha helices. Okay, of course, when do you form beta sheets? When do you form alpha helix? That depends on your R group. Okay, depends on your R group because your R group restricts the angles that are available to your peptide bonds. Okay, available to the C alpha to the carbonyl and C alpha to the nitrogen. Okay, so the R groups will decide that. Okay, so then if you have a sequence of amino acids that tend to have or angles that are on the top left, then usually they will be likely to form beta sheets. Right? 所以这个 plot 其实可以给我们很多 ideas as to protein 就是里面 amino acid 的这个 angle. Okay? 假如说你今天这个 amino acid 它的因为 R group 可能很大或者怎样，它会 restrict 你可以有的 available angle. Okay? 但它就会比较容易去形成某一些特定的 structure. Of course, 但还是你不能只看单一 amino acid, 你还需要去看说附近的其他的 amino acid 长什么样子。Okay? This is a table of summary of allowed phi and psi angles for some polypeptide secondary structures. Okay? So we're going to have beta strands, or essentially beta sheets, alpha helix, and we'll talk about this thing called 310 helix, and then this polypeptide 2 helix. And you can see how they have different phi and psi angles. But what you do notice is that they happen in a small range. Okay? For example, your psi angle, you have like minus 70 to minus 60. It's quite small. Okay? So that's the angles that are available for this particular structure. The secondary structures that we'll talk about are the helices and the sheets. Okay? And then we also have turns. Okay? We'll talk about turns in a little bit too. Most frequently observed secondary structures are alpha helix and beta sheets. So in a protein model that you see in journal articles or online telling you, this is the structure of this particular protein. When you see the ribbon-like thing, that's usually alpha helix. And the arrow thing, remember we saw earlier today, we have ribbons, and then we have like a little arrow, right? So this is ugly, but just, bear with me, okay? This is helix, and then this is talking about your beta sheets. Really, you see a lot of these, all right? These secondary structures are stabilized primarily by the hydrogen bonds between amino hydrogen and the carboxyl oxygen. Okay, so keep this thing in mind. Okay, so all of the secondary structures that we're going to talk about, they are stabilized, meaning they are capable of forming this structure is really primarily due to the hydrogen bonds and the regular hydrogen bond pattern between the amino hydrogen and the carboxyl oxygen. Okay, so regardless of a beta sheet or alpha helix, this is how it is. Okay, the reason why they can form secondary structures is because of the hydrogen bonding. Because without hydrogen bonding, your molecules does not want to be in a particular structure, right? If you don't have something that stabilizes it, it wants to freely rotate. And enzymes, we know, do not freely rotate, okay? It moves, yes, but not like completely random, okay? Not into a weird shape. All right, we will also discuss several other secondary structures in addition to alpha helix and beta sheet. We'll talk about the 310 helix, the pi helix, the polyproline helix, okay? And in beta sheet, we'll talk about how they're anti-parallel sheet, parallel sheet, and then we'll also talk about turns. Turns are used to change between structures. For example, one beta sheet, when it comes back, okay, into another beta sheet, those between this going this direction, coming back, you need to have a turn, okay? So we'll talk about beta turn. First, I want to briefly introduce the idea of helix. Okay, when we saw DNA, we also talked about helix. Okay, but in that sense, we're talking about double helix. But in proteins, it's just one single-stranded helix. Right? You don't have base pairing, right? So it's a single-stranded helix. Now, again, we have the helix rise, and what it is, helix rise, H, is the distance between each residue N. Okay, so each residue N, we have a rise. So between this amino acid residue and the next amino acid residue, the difference in height, that we call rise. And then we also got this thing called pitch. Okay, pitch is the distance between each turn, meaning the distance in vertical distance between this amino acid and the next time another amino acid come back to the same location. That's one pitch. Okay, so that's the height between the identical position and then for it to make one full turn. Okay, make sense? All right. So in above, these hypothetical structures show the effect of varying the number, okay, polypeptide residues per turn of a helix. So if you have a right-handed helix where n is equal to 4, then your helices are right-handed. So from this position, you have 1, 2, 3, 4. Okay, so 4 amino acid away, you come back to the same location, sort of. So that's like n equals to 4. Same thing here. You have 1, 2, 3. Okay, so it's 3. If you have 2, okay, n equals to 2 per turn, so this is per turn, then it's not even a helix. Okay, it's just a flat ribbon. So it's going to be completely flat because it's 1, 2, and then 1, 2. Okay, so it's always like that. So you don't have a 3-dimensional depth. Okay, so it's just 1, 2 comes back to the same location. Okay, so for every turn, how many amino acids are there that gets you back to the same location? Okay, so that's what it means, right? So number of polypeptide residues per turn of a helix, that's n. Okay, so that's how we say you have a helix, n equals to 4, helix, n equals to 3. Okay, as you can see, the larger the n, the smaller the pitch. Okay, that makes sense because the larger the n, that means the more distance. So if you're thinking in terms of a plane, the more n you have, you can go depth instead of go in the vertical direction.